On September 16, 1943, over the dense, tropical skies of Bougainville in the Solomon Islands, First Lieutenant Kenneth Walsh leaned over the controls of his F4U Corsair, squinting through the scratched plexiglass canopy as he meticulously recorded observations in his flight log, aware that the details he noted could mark a pivotal moment in the evolution of Pacific air combat. The Corsair, with its unprecedented speed and heavy armament, had already surpassed the nimble Japanese Zero in raw performance, yet hitting a maneuvering enemy in dogfight conditions remained a nearly impossible task. Deflection shooting, the art of predicting where a target would be at the instant bullets arrived, demanded split-second calculations that even the most seasoned pilots struggled to perform under the stress of combat. Walsh had mastered these calculations through instinct, experience, and relentless repetition, becoming the first Corsair ace in May 1943 with 6 confirmed victories, a feat few pilots could match. Most Marine aviators, however, arrived in the combat theater with only a few hundred flight hours, their training limited and often inadequate to handle evasive Japanese maneuvers. The standard Mark 8 reflector sight offered no assistance beyond a fixed aiming reticle, leaving pilots to rely entirely on intuition and hard-won experience, a gamble that often left rounds harmlessly trailing targets across the vast Pacific. Across the Atlantic, British engineers had already solved this problem with the 2 Malawian Kwacha's Gyro sight, a revolutionary device employing spinning gyroscopes and precision mirrors to automatically compute lead angles for moving targets, effectively compressing years of training into mere hours of instruction. Recognizing the profound potential of this innovation, the United States contracted Sperry Gyroscope Company to produce the Mark 18 for Navy and Marine Corsairs, while the Army Air Force adapted the design as the K-14 for P-51 Mustangs and P-47 Thunderbolts in the European theater. Larger and more complex than the compact reflector sight, the Mark 18 integrated 2 gyroscopes to measure pitch and yaw, translating aircraft movement into precise mirror-driven reticle adjustments that automatically positioned the aiming point ahead of an enemy in motion. Pilots set the target's wingspan and range using intuitive controls, and the sight calculated deflection almost flawlessly, transforming previously frustrating engagements into opportunities for consistent, lethal first-pass attacks. By late 1944, Corsairs equipped with the Mark 18 joined carrier operations aboard the USS Essex, with squadrons like VMF 124 and VMF 213 proving the system's indispensable value during missions over Formosa, the Philippines, and later Okinawa in Operation Iceberg, where relentless kamikaze assaults pushed pilots and technology to their limits. The gyroscopic sight enabled pilots to engage multiple targets in rapid succession, conserve precious ammunition, and allowed less experienced aviators to achieve combat performance on par with seasoned veterans. Japanese intelligence quickly realized that traditional reliance on maneuverability alone could no longer guarantee survival, and a doctrinal shift toward hit-and-run tactics reflected the discomforting reality that American fire control technology had fundamentally altered the battlefield. The Mark 18 was not merely a tactical tool. It embodied the apex of American industrial and engineering capability. Precision-machined gyroscopes, modular assembly techniques, forward area maintenance practices, and ergonomic cockpit integration, combined with tailored pilot training, produced a system capable of reliable operation under the extreme conditions of aerial warfare. The sight compressed the learning curve for deflection shooting, turning an almost mystical skill into a repeatable and teachable technique. Pilots like Lieutenant Robert McClure leveraged it to score victories with unprecedented consistency, while veterans such as Walsh transitioned from instinctive, experience-driven gunnery to technology-assisted combat, shaping tactics and doctrines that would carry forward into post-war aviation. The legacy of the Mark 18 extended far beyond World War II. It influenced Corsair operations during the Korean War, established foundational principles for radar-guided fire control, and foreshadowed modern automated targeting systems. Its success did not rest on glamour or a single brilliant invention but on systematic, practical problem-solving. Engineers devised the technology, production workers built it at scale, logisticians delivered it to remote forward areas, maintenance crews ensured operational readiness, and pilots employed it effectively in combat. The Mark 18 bridged human skill and mechanical computation, laying the groundwork for a new era where machines could perform calculations faster and more reliably than human minds, a principle that continues to define aviation and weapons systems today. In the broader historical context, the Mark 18 exemplified the cumulative power of incremental technological improvements applied at scale. While the Corsair itself was already a formidable aircraft, the gyroscopic sight amplified its lethality, making deflection shooting predictable and enabling pilots to operate with greater confidence under the chaotic conditions of war. The device did not make aerial combat safe or easy, but it removed one of the most difficult variables from the equation, allowing pilots to focus on tactics, situational awareness, and the myriad other challenges of high-speed dogfighting. Combat effectiveness increased, ammunition conservation improved, and mission outcomes became more reliable. From its meticulous design and rigorous production to its tactical application and eventual influence on post-war air combat doctrine, the Mark 18 gyroscopic gun sight stands as a testament to American ingenuity, industrial capacity, and systematic problem-solving. It transformed the Pacific Air War, not through spectacle, but through practical, measured, and reliable technological progress, proving that success in aerial combat often hinges on the intersection of human skill and well-engineered tools, a lesson that continues to resonate in modern warfare.